Hi everyone, welcome to the webinar for tonight. I will start talking even though a few people are still entering from the waiting room, just because I've got a few introductory slides before we hand over to Tom to speak tonight. So we will be having Tom Rayment from DUG Technology speaking on multi-parameter FWI imaging, high resolution imaging directly from raw field data. So the ASEG acknowledges the traditional owners of the land on which we gather today and the many lands on which we undertake our work. We recognise their continuing connection to these lands, water and culture, and pay our respects to their elders past and present. I'd like to thank our corporate members, our Corporate Plus, High Size, Total Seismic and Vel Size, and our corporate members Southern Geoscience Consultants, AGS, Santos, Transparent Earth Geophysics, Instrumentation GDD Inc., and last but not least, DUG Technology, who Tom will be joining us from today. I'd also like to thank our branch sponsors from WA and South Australian Northern Territory, who helped to enable our local branch events in WA and South Australia. Just a little bit of housekeeping. So you can ask questions throughout the talk using the Q&A function, and we will answer those at the end. Alternatively, if you would prefer to ask the question out loud, you can use the raise hand function when we get to the questions at the end. Webinars are free for anyone to attend, but I would just like to remind you of the member benefits of joining the ASEG. So you will get free access to our Exploration Geophysics Technical Journal, which has high quality geophysics articles, case studies, methodological studies. A free copy of Preview magazine, reduced entry to the AEGC conference. Our next one is in April in Brisbane next year. And free and discounted entry to regular social, technical events and travel scholarships, research funding opportunities for students, along with free membership for students and discount membership for retirees and recent graduates. We do have a Facebook, Twitter, LinkedIn profile, and you can check out most of our past webinars on our YouTube channel, which is where this video will end up as well. So now I'd like to hand it over to Tom to present. So just to give a quick introduction on Tom first. Tom graduated in 2004 from Imperial College in London with a bachelor's degree in applied mathematics. He began his career at Fugro Seismic Imaging before joining Down Under Geosolutions, DUG, in 2013, where he helped start the company's new EAME services division. In 2020, Tom took up the role of Chief Geophysicist. He's heavily involved in the research and development of processing and imaging technologies at DUG, including deblending, FWI and FWI imaging, least squares migration, as well as OBN and time-lapse processing. So with that, I will stop sharing my screen and welcome Tom to the ASEG webinar. And I'll turn my camera off and hand it over to you. Thanks, Tom.
Thanks, Kate. I can't share at the moment. I've got host disabled participant screen sharing, sorry.
How about now?
Perfect.
Thanks, sorry.
No worries. Okay, thanks, Kate. Hello, everyone. Good afternoon, good evening. Today, I'm going to be talking about how we can use FWI to get high-resolution seismic images directly from field data. The motivation behind this work is pretty straightforward. Our clients want better data faster, and those ideals drive our research and have led us to the work that I'll be describing today, which uses FWI to deliver fully imaged, high-resolution seismic data without the need for any pre-processing. Now, the conventional seismic processing and imaging workflow consists of a multitude of steps, each of which need to be tested and applied, usually in a linear fashion, with the next step only starting after the previous one is complete. So here I'm showing a fairly standard workflow for a marine data set. Now, each of these steps, of course, has many sub-steps, and each of those has a wide range of parameters that need to be tested and applied. And as a result, processing seismic data can take many months or even years, depending on the size and complexity of the data set. And further, the parameter space for this kind of flow is enormous, and navigating through this space relies on many subjective judgments to reach a desired outcome. And those outcomes can vary drastically depending on the decisions made during that flow. But what we can do now with our latest FWI technology is to bypass that lengthy and laborious workflow and use FWI alone to generate interpretable images without any of the processing steps described in the conventional workflow. And as a result, we can drastically reduce the turnaround of a project. But this approach also allows us to get better results, and we'll see some examples of that later. But first, let's remind ourselves of how FWI works. And in essence, it's a fairly simple process. We take some initial guesses about the properties of the Earth, and this is more often than not just a simple velocity model. We then simulate the seismic experiment in the computer, and we produce some synthetic data. We then compare that to our field data, and that point is important. We're replicating the seismic experiment in full, and that includes modeling of multiples and ghosts, and then comparing that with the data essentially as it was acquired in the field. And from that comparison of these two data sets, we can determine how we need to update our initial models to make a better match between the two. And then we iterate around many dozens, tens or dozens of times until we converge on an acceptable result. Now, traditionally, FWI has been used solely for model building as part of the conventional workflow, most commonly to update velocity models using diving waves only. But multi-parameter FWI updates are now much more common, and that allows us to solve for other quantities such as anisotropy or even Q as part of these simultaneous inversions along with velocity. Here are a few examples of before and after the application of these multi-parameter FWI inversions for these other parameters. But let's just have now a quick look at an example of a conventional diving wave FWI for a velocity update. So this is an example from a hybrid tow streamer OBN project in offshore Norway, fairly shallow. And there's some high resolution streamer data that was acquired at the same time as the sparse OBN data. The streamer data is migrated here with an initial model, which is overlain on top of the image, and we can see a slice at 800 meters on the left. Now, this data had this sparse set of nodes, and that allowed access to up to 15 kilometers of offsets. And that's really useful for diving waves. That means we get a deep depth penetration of diving waves, allowing us to get a velocity model update very deep indeed. So this is the starting model that went into diving wave FWI, and this is the model that was generated using these long offsets in diving wave FWI. And you can see that we get a very deep update down beyond 5 kilometers as we toggle between the input and the output. So a nice deep update thanks to those long offsets. What we also see in this example is how FWI is able to capture many of the details in the velocity model, especially associated to what some of these injectites in the shallow, and how that drastically improves the imaging, especially around this zone here, before and after migration using the updated velocity model from FWI. And on the left, we can see the spatial resolution that's introduced through the FWI process. We can see the initial model is fairly smooth, and a lot more detail is introduced after FWI, including some shallow channels up here and a clear change in velocity across this change in orthology here. So that's a very conventional approach to using FWI to update velocity and using diving waves only. This example is slightly different, is because we have these very sparse nodes which allow us to use diving waves to a much deeper down much deeper than we traditionally would do. So we know that diving wave FWI can provide very accurate and detailed models, but it tends to use just a small fraction of the data. So here's a shot record that went into the FWI that I have just showed. And now this slide highlights the diving waves that we used in that inversion. And as you can see, there's a lot of information in red that has been muted out and is just simply unused in FWI. This small gray strip is the amount of data that was used to generate that update. So those are the diving waves. But of course, we have the data that was muted out, and these are, of course, the reflections. So the question is, can we do more with FWI? How can we use this data? What about in scenarios where we don't have sparse nodes and we don't have a diving waves which penetrate to the targets that we're interested in? Can we use the reflections in those instances? Now, including reflections in FWI opens up some interesting possibilities. So far, we've seen that FWI can be used at low frequencies to generate models for use in the conventional workflow. But what we're going to look at now is using reflections in FWI at high frequencies to try and derive interpretable products. This is something that we've been investigating now for about 6 or 7 years. And I'll be discussing some of the products that we've generated along that journey, from a velocity attribute to pseudo-reflectivity, then to P impedance, and up to our latest multi-parameter inversion for velocity and what we call intercept reflectivity. So we start back in 2016. Back then, we took this initial model from a data set which was spanning deep and shallow water, and we fed it into a 2D full waveform inversion. And we opened up the mute to include reflections and ran FWI up to 100 Hertz. And that produced this image. And what we can see is the same color gradation which is associated with the velocities that was present on the input model that we see here. But also we see an imprint of a higher frequency, high frequency geological features. Now this is not a true velocity model, and we'll discuss why later, so we call it a velocity attribute. But what it does, it provides a detailed image of the subsurface, and this has been generated from field data, and it's used primaries and multiples and ghosts to create this image. So here's a 3D example of the same approach, this time up to 50 Hertz, and this is from a fairly deep water data set. And again, we see the detail in this velocity attribute that we can directly interpret with some complex structures in the midsection and a number of thin layers in the shallow and the deeper sections. And shown on the right is a high resolution depth slice, which shows some clear changes in geology. So already this is pretty impressive. We've derived something that we can directly interpret from the field data using FWI. But what if we want to interpret something that looks a little bit more like seismic? And that brings us to pseudo-reflectivity. So here again is that 50 Hertz velocity attribute. Now what we can do is take the derivative of this model, which is essentially just a low cut filter and a phase rotation to produce a pseudo-reflectivity volume, which looks something like this. So let's just compare those two results. We're going from this velocity attribute, we're applying a process to this, and we're getting a pseudo-reflectivity volume. And this immediately reveals more detail, both through the inline shown on the left here and on the depth slice on the right. And indeed, it contains all the features we'd expect to see from a result of a conventionally imaged data set. And there have been a lot of very impressive examples of these pseudo-reflectivity volumes presented recently to very high frequencies. And we'll discuss why we call it a pseudo-reflectivity shortly. We didn't want to stop at pseudo-reflectivity. In 2019, we developed a method to generate P impedance using FWI. This is the relatively simple workflow we use to do it. The velocity attribute that we saw earlier can be thought of as a combination of low frequency kinematic components and a high frequency dynamic component. Now we assume that the low frequency kinematic component to be a pure velocity, and to get the acoustic impedance, we therefore need to incorporate a low frequency density model, which we built from the well information. The high frequency part of our velocity attribute already contains a contribution from both density and velocity effects, and is a scaled version of a relative P impedance volume. So by recombining these two branches, we can then derive an estimate of P impedance directly from the velocity attribute model. So here again is our 50 Hertz velocity attribute, and here is the P impedance volume derived from it. Again, just toggling between the velocity attribute to the P impedance model. Now the well overlay that we can see here, this contains the absolute P impedance log, and it shows a pretty good match at the well location. It's worth bearing in mind that these results have not been explicitly calibrated to the wells, and therefore the detail in the match at the well is equivalent to a blind QC of our volume. But we can compare this to a conventional AVA inversion workflow, which is something else that we did in this experiment, and that's here. Now this workflow involves generating angle stacks from conventional imaging, building low frequency models, the extraction of wavelets, well calibration, and then a simultaneous inversion. Now the match at the well is also good, but we should remember that this result includes wavelets which have been extracted at the well locations to give the best time. Now as we toggle between these two results, you can see they share some similarities, but there's also a difference between the two volumes. It's not necessarily clear which is the best in all cases, but it goes to show that this FWI workflow showed some promise and achieved it in a fraction of the time that it takes to generate conventional P impedance volume. Now that's nice, but all the results I've shown so far are from what we call a single parameter full wavefield inversion. And what does that mean? Well, when we're including reflections in FWI, we have two phenomena to handle. One is the kinematics, which is essentially the move out, and that's governed by a smooth background velocity field. The other is the dynamics, or the amplitudes, which are governed by a reflectivity generating field. Now, the single parameter inversion makes no attempt to distinguish between these two effects and combines both into this velocity attribute field, which is here. And this is why we see this combination of velocity and also reflectivity effects. And that's the reason we call it a velocity attribute rather than a velocity. Then the next step is to compute the pseudo-reflectivity, which is derived from the velocity attribute. And it's generally not suitable for amplitude analysis, again, because this is a single parameter inversion and we're combining effects in the FWI. Now, our experience of these approaches is that they can provide excellent fast-track structural stacks. However, the models we generate may well be ill-suited for conventional imaging, especially in regions where our prior assumptions about density can diverge from the truth. And this limits the benefit of such models. And can we trust the amplitudes of these outputs? Well, we achieved a nice result from our P impedance volume, but we did make some fairly crude assumptions when we split the model into velocity and impedance. And we also used well information to generate a low frequency density model. So these are the problems that we're now attempting to solve, and that brings us to our latest technology, which is a multi-parameter FWI imaging technique to simultaneously generate velocity and reflectivity outputs. In essence, this is what we're trying to do, moving from this two-step single parameter inversion to a one-step multi-parameter inversion, through which we can now produce independent velocity and reflectivity models. This gives us a velocity which is a pure velocity and a reflectivity which is fit for interpretation and amplitude analysis. And importantly, this has been generated in a manner similar to a least squares RTM, but with the important distinction that it's derived by finite difference modeling and it's using primaries, multiples, and ghosts. Now, I'm going to give you a warning. There's some maths coming up. That's going to split the room pretty drastically, I imagine. I apologize. There's only a few slides. It's I've tried to simplify it as much as possible, but I think it's useful to try and understand how we're doing this. So this is the acoustic wave equation. We won't go into too much detail, but the basics here are that it contains information about density, velocity, how the wave field behaves in space and time, and also a source term. Now, what we can do is apply some basic operations, move some terms around, and get this version of exactly the same equation. And the reason we do that is because it highlights this term here, which controls the amplitude of reflections. That's the dynamics. And what we notice is that this term looks very similar indeed to the one below, which is derived from the intercept term of the FWI equation, a classic intercept, seismic intercept volume. So we know that the term highlighted in the first equation controls the dynamics. So what we can do is replace that with any scattering term we wish, such as this intercept reflectivity, which we've highlighted in red here. And this gives us an augmented acoustic wave equation. Furthermore, these terms provide the scattering interface needed to generate the so-called rabbit ears, a tomographic term, or as we prefer to call them, the RU ears. So this is the classic FWI kernel. It contains contributions from the diving waves, which is given by the banana. The RU ears term is the reflection tomographic update, and we also have the migration smile as shown here. So this gives us a mechanism in this formulation to also update not just for this intercept reflectivity term, but also for velocity too. And so we can then solve for both of these as part of a multi-parameter full waveform inversion. However, it's not quite that straightforward. There exists significant crosstalk between these parameters and also relative scaling issues, which require special attention during the optimization stage of FWI so that we can separate the quantities which we wish to derive. Now, I won't go into the technical details of our scheme, but suffice to say it's a vital part of the inner workings of this implementation of FWI, and it's described in detail in the paper which is referenced here, and I'll also be showing that at the end. So using this scheme, we can now produce independent velocity and what we call intercept reflectivity models. And this gives us a velocity which is a pure velocity and an intercept reflectivity volume which is fit for amplitude analysis. And those are the two really important things that we're trying to get out of this technology. So let's have a look at this new method in action. So the data I'm going to show is from the Australian Northwest Shelf, located about 115 kilometers northwest of Barrow Island. It was a conventional towed streamer, marine towed streamer survey acquired using a dual source H streamer configuration with a maximum offset of 6 kilometers. So we fed the field data and a starting model into our new FWI algorithm, and we inverted for these two outputs, the intercept reflectivity and the velocity, and we did that up to a maximum frequency of 85 Hertz. Now, to generate a comparison, what we did is at the same time, we took the field data, we went through conventional time processing, and we depth migrated that data with the same FWI velocity so that we can generate a stack, which would be a direct comparison to our intercept reflectivity from FWI. Now, this is a fairly deep water data set, and we have a relatively smooth initial model, which was derived from the legacy velocity model. Now, the FWI started at 15 Hertz. We might think that starting at such frequencies poses a risk of cycle skipping, but our observations so far are that reflections are far less sensitive to cycle skipping than diving waves. This is a TTI FWI, and our SOCHP was not updated during the process, but it's certainly possible to do so. Delta can be updated in a conventional fashion since we produce images from which we can tie events to well markers. and epsilon can be simultaneously inverted either as an initial velocity and epsilon inversion, or even as a 3-parameter inversion. We ran the FWI at 15 Hertz using just 1/8 of the shots, and then increased that number as we went up to 85 Hertz, where we used all of the available shots. And both the Kirchhoff that we're going to show, the Kirchhoff migration, and the FWI will run using a 3-kilometer half aperture. So let's have a look at the first of these two outputs that we get from this approach. First of all, the velocity output. Now here's our input velocity model that went into this process. It's a fairly smooth velocity model derived from the legacy velocity model, and we can see an inline, a cross line, and a depth slice through that initial model. Now here's the velocity model after we've run FWI up to 85 Hertz. And I'll just toggle between those quickly, the input model and the FWI model. You can see there's a lot more detail introduced, including some thin layers through this section, capturing some high velocity contrast, which is especially apparent on the cross line. And we can see a lot more spatial resolution introduced between the, when we compare the initial model to the updated model. Now, what's important about this FWI model is that it's, as we said earlier, it should be fit for conventional imaging purposes, and we'll see that in a second. But also you can see there's no imprint of that reflectivity on this model. It's a fairly smooth, low frequency, low wave number velocity model, which is what we expect when we split out the effects of kinematics and the dynamics. Now, we said that we want to get velocity models out of this process that are fit for conventional imaging. And here's an example to show that that is indeed the case with this technique. So this is our input model that we've just seen, our smooth legacy velocity model. And this is overlain on a Kirchhoff migration of some pre-processed data on the left here, with the well and the velocity profile shown here, as well as here we have the initial velocity in red and the check shot in black. And on the right-hand side, we have the image gathers using this velocity model. And what you can see is it's not particularly accurate. There's a reasonable amount of move out on these gathers, and we can see that the velocity model isn't matching the check shot particularly well at depth. Now here's what these images look like once we migrate using our model derived from 85 Hertz FWI using reflections. And what you can see here is that the image gathers are flattened, which is an excellent sign to show that our velocity model is accurate. We have a better tie to the well, especially down at depth, way below the diving wave limit. And we can see a simplification of structures at depth associated with resolving the velocity variations, lateral velocity variations in the overburden. So I'll just toggle between those two images again. So the initial model and the migration using the updated model. Again, we can see flattening of this event here. And we can see a much improved well ties, as I say, especially at depth, and flatter image gathers. So this just goes to show that this approach is fit for conventional imaging, should we wish to use it for that purpose. Now, we don't need to run to 85 Hertz to get such a model. We can get a similar result when we go to 20, 30, or 40 Hertz. So we can look at the same results just through a couple of depth slices here, the starting model and the migrated data at 1.9 and 2 kilometer depths. And here is the result using a new approach with just this velocity model. And you can see the big increase in spatial resolution, picking out a number of details, especially in this region here, as we correlate high velocity contrast to changes in geology. So again, that just shows this approach generates a model which is appropriate for conventional imaging should we wish to go that route. However, what we're saying is that we don't necessarily need to, because the other thing that we're outputting from our FWI approach here is this Intercept reflectivity volume, which is a volume which we can use for analysis and interpretation. So let's have a look at that now. So firstly, this is the Kirchhoff migration we've just seen using that 85 Hertz FWI velocity model. The input data of all available shots have been passed through a conventional processing and imaging sequence, which includes deghosting, designature, demultiple, regularisation, and then an 85 Hertz Kirchhoff depth migration. So this is a result of a conventional workflow. Now the next slide is the result of our FWI workflow. This is the Intercept reflectivity volume that we get from our 85 Hertz FWI. And I'll just toggle between those slowly. And what we can see, first of all, is that the result is remarkably similar to the conventionally imaged result. But the Intercept reflectivity has been derived directly from the field data. Now, there are no multiples or ghost energy present in this section here, which means that FWI has essentially performed deghosting, designature, demultiple, model building, and least squares imaging in a single step. This is a least squares imaging solution, which means we get a lot more detail and resolution compared to the conventional workflow, which is shown here. And we did that directly from the field data. So I'm pointing out a couple of areas here which are quite interesting on these comparisons. There's a little pinch out feature here. There's some imaging issues in the conventional image underneath the fault here. And there are some high frequency thin layered bedding on the right hand side here. Now, when we go to the conventional image, we can see that this pinch out is not as well imaged. There are some fault shadow issues with the conventional imaging, and the resolution is somewhat lacking on this cross line compared again, sorry, to the FWI image, which is here. So again, I'll just toggle between those so you can see the differences in imaging between this is the conventional image and this is the FWI image. Conventional and the FWI. So let's have a look at some slices as well, because one of the most obvious improvements of this technology is the increase in resolution, both temporally and spatially. This is a slice at 2.5 kilometers using the conventional workflow, and this is the result using the FWI workflow. So again, I'll toggle between those, and you can see immediately there's a drastic increase in resolution using the FWI workflow, and that's because it's a least squares imaging solution compared to the Kirchhoff migration, which of course is not. This is slightly deeper at 2.7 kilometers, and this is a really nice example of where the FWI imaging solution gives us not only an improvement in resolution, but also reveals more details that were simply not apparent in the conventionally imaged data set. So at 2.7 kilometers of depth, we can see there are some hints of some channel features in this region here, as well as a channel which runs from north to south down here. But you can see it's somewhat obscured in this region by some noise which is cutting across, as is the case for this other region here. This is the conventional image, and this is the FWI image. And you can see in those two regions that I just highlighted a drastic change in imaging, much clearer hints of these channel features which are coming through here, and much clearer imaging of this channel feature again on the right hand side here. So the conventional image and the FWI image. And again, we see that drastic increase in resolution, which we saw earlier. So we're getting better results from this approach than we do from the conventional imaging workflow. A few more examples now. This is zooming in to the shallow section. This is a slice at 1.5 kilometers through this fairly complex zone here. This is again the conventional imaging, and this is the FWI imaging. We can see an increase in temporal resolution on the left, much more detail, especially underneath the seabed and through this region, and that's borne out by the depth slice, which shows a drastic increase in resolution. Many more details in this FWI image. Slightly deeper down now through a fairly heavily faulted section here at 2.5 kilometers. This is the conventional image, and this is the FWI image. The conventional image and the FWI image, again, much more resolution and also revealing faults which were simply not apparent in the conventional image. And again, this image has been generated directly from the field data using FWI in a fraction of the time it took to generate the conventional processed image. Now, the comparison between Kirchhoff and FWI imaging is maybe not fair. As we said, the FWI image is generated in a least squares manner. It's a least squares imaging solution, whereas the Kirchhoff is not. So it's perhaps a fairer comparison to look at least squares RTM, and that's what we did. So we took the field data, we went through the time processing sequence as described, and then we ran an 85 Hertz least squares RTM, and that's shown on the right hand side here. And you can see the comparison between the Kirchhoff image on the left and the least squares RTM on the right is pretty dramatic. The least squares approach gives a much more detailed and higher resolution output. Now let's compare these two both to the FWI result. So on the left, as we toggle here, we're looking at what we just saw, the comparison between the Kirchhoff image and the FWI image. On the right now, we're comparing a least squares RTM image versus the FWI image. And again, we can see even here, using the most modern imaging technology we have, the FWI image is still improving upon the least squares RTM. There is more detail and more resolution in the FWI image compared to least squares RTM. Now, a quick side note, an additional product that we can generate from this FWI imaging process is what we call horizontal reflectivity, which is shown here on the right-hand side. This horizontal reflectivity is shown at this 2.5 kilometer slice, and the standard seismic is on the left here. And this allows for highlighting complex changes in lithology, such as across faults or channel features, and much like diffraction imaging that we might, a result that we might get from diffraction imaging, which is a nice additional output from this approach. So I want to show another example here just to demonstrate the power of this FWI approach to handle multiples. So this example is from a shallow water data set where obviously multiples are much more of a problem. This is now only to 20 Hertz just to demonstrate this effect. And we're going to look at the Intercept reflectivity volume derived from this process. So at the very beginning of this inversion, the FWI knows very little to nothing about the reflectivity of the subsurface. So at the very initial iterations, what it does is it puts everything into that reflectivity volume. So that's source signature, ghosts, and multiples. So the early iterations, such as this one, we see a pretty confused image, which contains primaries as well as multiples. And I've highlighted a lot of those multiples in red here. Now, as FWI works through the inversion and iterates, it realizes that these multiples simply cannot be in the reflectivity model, because when we generate field data using this reflectivity model, we don't get shots that match our field data. So it gradually removes them from our reflectivity model. And this is the result after many more iterations. And you can see that those multiples have disappeared. So we toggle between the early iteration and the later iteration, those multiples have gone, and we're left with just the primary and also no ghost or no signature in our reflectivity model. Now I'm going to show a video of this in action, going from iteration 2 to iteration 20, so we can gradually see how these multiples are removed. So here's iteration 2, and here we are moving slowly through iterations and seeing this Intercept reflectivity model change, and seeing those multiples disappear, leaving us just with the primary. Now I'm going to do it again. I recommend that you fix your eyes on one of these multiples that I've highlighted in red, so you can see how, as we move through the iterations here, they gradually disappear. And again, we're left with just the primary. So this is the power of this technology to remove multiples from our reflectivity models. So we've seen that we can achieve this workflow on the bottom, this FWI workflow, and we can do it in a matter of weeks rather than months. Now, it can happen alongside the conventional workflow. We can use the velocity updates from the conventional imaging, as we've seen, but we also get this full wave field least squares image for free through this process. However, there's one other thing that we get from the conventional workflow, and that is AVA products. So what about AVA? Well, what we can also generate from this process are angle stacks. So here's a comparison of the conventional workflow to generate near, mid, and far angle stacks. This again is at 85 Hertz. And here is using our FWI imaging technologies directly from the field data to generate very similar near, mid, and far angle stacks. And I'll just go between those, and you can see, again, the two look remarkably similar. The difference, though, being the FWI approach didn't require any pre-processing and was achieved in a fraction of the time. And in fact, I think the FWI images are slightly cleaner, especially as you can see on the near angle stack in the deep here, before and after. Sorry, not before and after. The conventional imaging and the FWI imaging. Now we can make those angle stacks now, but the next step and what we're working to achieve now is not just to generate angle stacks, but to directly invert for gradient reflectivity too as part of this approach. So a 3-parameter inversion for the velocity, the intercept reflectivity that we've seen so far, but also directly inverting the gradient. Quickly coming back to our maths, the way that we do that is, if we recall our augmented wave equation, but there's nothing to stop us adding a gradient-like term, as well as the intercept term, which we're showing here. So the intercept term is in red, we saw that previously, the gradient term is now in blue, which, as you can see, includes a directivity component, as we would expect. And we don't need to stop at 2 terms. We can use as many terms as we wish to include. For example, the AVA curvature term. So as long as we have a scattering and directivity component, we can generate a desired amplitude response. So it is possible to get intercept and gradient from this approach. We'd usually assume that we need the elastic wave equation to produce these outputs. But here I'm showing a synthetic AVO class 3 response generated by the elastic wave equation on the left and via our augmented acoustic wave equation on the right. Now the result is very clearly very similar, but our new approach produced this result in about 1/10 of the time, 1/10 of the compute cost it took compared to the elastic FWI. So this is the next step in this approach to compute this gradient, as well as the intercept, and one we're working on now. So like I said, we've seen it's possible to achieve the workflow going from field data into FWI to get an interpretable product. We've seen we can use marine, land, and OBN. We can use multi-survey inputs. And what FWI is able to do is perform deghosting, designature, free surface demultiple, interbed demultiple. It can also perform the model building, inverting velocity and isotropy Q, and it performs least squares imaging to get a fully imaged product. And these are our intercept reflectivity outputs and also AVA products. And this is what we're trying to build towards. We're trying to build FWI towards a new platform for processing and imaging, such that all of the processing and imaging challenges can be dealt with directly within FWI. So that brings us towards our conclusion. We've developed this simultaneous full waveform inversion for velocity and intercept reflectivity. The image we produce is similar to that of a least squares RTM, but it's using the primaries, multiples, and ghosts, and the output is fit for amplitude analysis. And it's all happened directly from the field data using a smooth initial model. And on top of that, in the near future, we also hope to invert the gradient as part of this approach, but we can also right now generate angle stacks. So more information can be found on this technology in a paper that we presented in the at the EAG last year, which I'll reference in shortly. So this is what we wanted to do. We wanted to get better results faster, and we believe this technology is capable of doing that using our multi-parameter FWI imaging technology. There's much more information available at these places here. This is the paper that I've been referencing for anyone who wants to go into more detail, and we'll be presenting more papers at this year's conferences too. So that brings me to the conclusion. Thank you very much for your attention, and I'll happily answer any questions.
Great, thanks, Tom. That was really interesting. And we have a few questions that have come through. So the first is from Boris Gurovich. He said, thank you. If you produce both velocity and reflectivity, you have density. Is this density from well data or from seismic?
It's from seismic. The process is actually generating both velocity, intercept reflectivity, and density updates as part of the FWI. So we get an updated density volume derived from the seismic.
Thank you. All right, the next one. Is your approach designed to satisfy users of the legacy technology?
Our approach can fit into legacy processing workflows, conventional processing workflows. It can sit alongside it, or it has the potential to replace it. That's in terms of the workflows. In terms of, I'm not quite sure if the question is legacy workflows or data, but it was also very applicable to legacy data, which is an important point anyway, that this can potentially yield new insights into existing legacy data, which have maybe reached a limit in terms of conventional workflow, but this extra resolution that we can generate from this approach may deliver fresh insights into some legacy data sets.
Great. Then we have a question from Andrew Long. Tom, interesting narrative and some nice looking examples, thanks. Your publication suggests that you make an assumption about a fixed density model within the method. How sensitive do you find your gradient amplitude results are to that density assumption? The synthetic comparison presumably used the correct density model. Do you have a gradient version for that real data to show too?
That's a good question. I'll have to come back to you on some of that, Andrew, but the synthetic was derived without any assumption about density. We don't yet have the results for deriving density, deriving the gradient from the results I showed earlier, but it's something we're working on. It's certainly a challenge, but we have some schemes that are proving pretty positive so far, and that's an avenue that we're currently investigating.
Cool. John Coffin said, nice talk. Have you tried this for land data?
We have, yes, and land data is always more challenging. There's a little bit of pre-processing that needs to happen with land data, so it's not quite from field data, but not too much. We just need to get a suitable handle on the wavelet. But so far, yeah, very encouraging results, and hopefully we'll be sharing some of those soon.
Cool. Boris, I think, clarified his question. Perhaps he said he means the Earth is not divided into dynamics and kinematics. Not sure if that helps.
No, I mean, the Earth is complicated. This is using the most advanced technologies we have at the moment. That doesn't mean to say that we don't need to push this towards elastic FWI in the future, and that's another avenue that we are investigating.
No worries. Sidi Mendy said, thank you for that great presentation. Can Doug do the processing and the FWI?
Yeah, I mean, like I say, it's very possible to run these workflows side by side and start the imaging and start the model building, the imaging, add on this technology to the end of the model building process. And like I say, you can use the velocity for conventional imaging purposes, but you also get this intercept reflectivity volume essentially for free, which is quite exciting because it's a least squares image using the full waveform. So the two can fit together. It's not necessarily one replacing the other, but that's what we're moving towards. Whether we can go directly from the field tapes to these intercept reflectivity images as rapidly as we can.
Another question from John Thornton. Is there a minimum far offset needed for this to work for the depths you showed?
Well, the sensitivity, the kinematic sensitivity will depend on the maximum offset you have, of course. So the more offset you have, the more angles you have, the more chance you have of deriving an accurate velocity model and therefore an accurate image. But